I need to tell you a little bit about even and odd functions. There's an algebraic definition of what an even function is. And the algebraic definition is as follows. F is even if when you substitute in negative x, you're going to get the original function back. I'll tell you what odd means. So F is odd if when you stick in negative x, you're going to get negative f of x coming back. So each of these terms have graphical implications. And what are these graphical implications? If a function is even, it remains unchanged when reflecting about the y-axis. So let me use Desmos to show you some examples. Okay. I feel like I should give you a couple seconds to copy that down. So let's see here. What's an example of an even function? Something like x squared. This guy is even. Okay. Now watch what happens if I replace the x squared with parentheses negative x close parentheses squared, I get the same exact graph back. Do you see? Here's the original graph. Here's the graph when I insert a negative, I got the same thing back. Okay. What's another example of an even function? Another example of an even function is cosine of x. Let's hide these guys. Okay. So first of all, when I look at this graph, I could see I could reflect it about the y-axis and I get the same graph. But if I were to check it using the software, I get y is equal to, I could just put cosine, and then if I insert a negative x here, I get the same exact graph. Can you guys see that? So here's the original graph. If I plot cosine of negative x, I get the same graph back. So this is an example of an even function. Okay. I can add two even functions. I still get an even function. So just to show you, if I have y is equal to x squared plus cosine of x, that's this black graph right here. This guy kind of looks like a parabola. It is also an even function. You can see it's symmetric about the y-axis. Okay. Is there any question about the even functions? I want to show you some odd functions. Simplest odd function is just y equal to x. Let me show you a few odd functions first. Y equal to x squared, x cubed, sorry. X to the third power. Whoa. Oh, I put x equal to, I need a y there. Oops. Okay. This blue graph is also odd. I'll show you one more famous odd graph. Y equal to sine of x. So cosine is even and sine is odd. And this is another example of an odd function. So can see that there. Okay. So these are all examples of odd functions. And I think let's work with x cubed for a second. Okay. What happens when I insert a negative x? So I'm gonna put in here y equal to parentheses negative x close parentheses cubed. I don't get the same graph back. I actually get the graph rotated. Okay. So that's one example. Let's take a look and see what happens if I did the same thing with sine. I have y equal to sine of negative x like this. I hit enter. So here's the original sine graph, the green one. Here's the one where I insert a negative x. Here's the original x cubed graph. Here's the one where I insert the negative x. So what ends up happening is if f is odd, then it remains f of negative x is the graph of y equal to f of x rotated 180 degrees. So all those pictures, if I just took this graph, if I just rotated it 180 degrees, I get this graph. Same thing with sine. If sine looks like this, I rotate it 180 degrees, I get it to look like this. I'm not flexible enough to do that well, but that's the basic idea. All that explanation was just to explain even and odd functions, which I didn't do a good job of explaining to my Tuesday, Thursday, 5A class, so I'll probably post a link to this video for them. But for this theorem, I haven't even told you the theorem yet. The theorem really requires that your limits of integration are negatives of each other. So notice limits of integration are negatives of each other. Okay. So so the best one is for the odd function. So let me show you the odd function one first. And I'm going to go back to my Desmos real quick. And I'm going to look at an example. So I think I'll just tell you right now, the example I'm going to program in is going to be the integral from, let's just do -2 to 2 sine of x dx. This is the thing I'm interested in finding. Okay. And I'm going to show you with the picture. So let's come back over here. We're not going to actually calculate the integral. I just want to look at the graph. So here's y equal to sine of x like this. How do I restrict it from negative? Does anyone remember how to restrict it from -2 to 2?
You have the braces. And,
This thing here, this guy?
yeah. And then
And
you
do I put a comma or no comma?
no comma.
Thank you.
And then you put the -2 and then less than or greater than x and stuff.
Okay. So I got this thing. I got -2, comma 2, and then I got to close that guy off. No. How do I get the right brace? Shift? Enter? I didn't like it.
You're supposed to use like the less than.
Oh, not interval notation. Got it. Thank you. Appreciate it. Okay. This thing with an X in there, I guess. Oh, it's gonna work. Perfect. You know what? I kind of changed my mind. I kind of want to go to pi. I think pi would be a more beautiful, interesting picture. I wonder if I just type in pi, if it's going to magically convert. Oh, yes. Pi. There. This is the graph I wanted to show you for sure. If you wanted to calculate the area under here, area under this curve, what do you think the answer would be, my friends? What's the area under the green curve? You just look at it, I think, and tell me the answer, right? Anyone? 0, Aram, for sure. I can't actually show you on the iPad. I could point at it, but you won't be able to see what I'm pointing out. But from 0 to pi, there's the positive area, right? And then from negative pi to 0 is exactly the same area, but below the x-axis. So as Aram is saying, when we talk about signed area, that signed area is going to be 0. Does that make sense to everybody? Can you guys see that? So in general, this integral is always going to be 0. So this is our nice little theorem. I kind of wrote too much all over here. It's like a giant mess. But whenever you have an odd function going from negative a to a, your answer is automatically 0. So that's the best. Now you still have to show it's odd by plugging in the negative x and getting negative f of x coming out. And I'll show you an example of that in a second. What about for the even one? For the even one, the result is still great, but not as great as the answer being automatically 0. For the even one, we can go from 0 to a, f of x dx, and then just multiply our answer by 2. So this is also good for you. The reason why this one is good for you is we love it when one of our limits of integration is 0, because plugging in 0 is easy. Aram says, what happens if you shift the graph to the left? Once you shift your graph to the left, it might not be odd anymore. So if you shifted it a full pi to the left, I think you'd be okay. But if you only shifted it like a little bit, then your graph wouldn't be odd. Your graph would be something else. I hope that makes sense, Aram. Maybe I could show you real quick. This graph is odd, right? It remains unchanged when I rotate by 180 degrees. I mean, not unchanged, sorry. When I rotate it, 100, yeah, when I rotate 180 degrees, I get the same thing. But what happens now if I were to insert, actually I need to insert a parentheses here. Parentheses, +1, parentheses like this. Once I've shifted this away, when I rotate this graph by 180, it's going to end up, there's no way I'm going to get the same graph. I'm going to get something like really weird looking. Okay, so I guess if I replace this with a negative x, it would look like this. Y equal to parentheses negative x +1 close parentheses raised to the third power. So like, it doesn't look like the original graph rotated 180 degrees. It looks like something weird. Okay.